Welcome back. We are talking about water treatment, and in this video, we'll be talking about the plain sedimentation aspects of water treatment. And the Stokes law is more important in the water treatment section. And in the previous videos, we have discussed Stokes law can be expressed as 418 SP minus SF d square 3t plus 70 by 100. D is the diameter of the particle. SP is nothing but the specific gravity. V is the velocity. So when you're using this equation, V should be in millimeter per second and D should be in millimeters. T is the temperature of the water. Conventional form of Stokes law is V is equal to 1 by 18 mu GT square of V minus rho W. This is in terms of absolute viscosity. Same equation we are writing in terms of kinematic viscosity. We are going to get this. So let us look the application by using a small problem. Calculate the settling velocity of the particle of 0.004 centimeter diameter. Specific gravity 2.67 at 25 centigrade. So here, when applying Stokes law, first of all, you should check whether the particle size is less than 0.1 millimeters or not. Because Stokes law is applicable for particles less than 0.1 m. It is less than that. So straight away we can proceed. Straight away we can proceed for that. The specific gravity is given as 2.67, and you apply the Stokes law, 418 d square, etc. 418, 2.67 minus 1 diameter. It should be converted in centimeter, it converted into millimeters. So 0.04 millimeters. And then 3 into 25, temperature of water is 25 plus 70 by 100. What you are going to get is 1.62 millimeter per second, which is equal to 0.162 centimeter per second. And here, second equation, if you try to use, what we need is absolute viscosity value we need. So in this particular case, we will assume the temporary absolute viscosity as 10 to the power of minus 3 Newton second per meter square from the standard data chart. Then we substitute all the values here. Here I'm converting the D value into meters because I'm going to put G in terms of 9.81. So therefore, I'm going to get as 0.162 10 to the power of minus 2 meter per second. 10 to the power of minus 2 centimeters means nothing but centimeters. Last equation, we need kinematic viscosity. Kinematic viscosity, you can find out from the temperature chart, or you can use the equation kinematic viscosity is equal to mu by rho. This equation also we can use this equation, and then we can also find out, or from the chart also you can use. So use this equation, you are going to get again 0.162 centimeter per second. What this indicates is we can use any of these equations depending on availability of the data to calculate the settling velocity of the particle. That is the most important thing we should understand. Then you're talking about the score velocity or displacement velocity. So in a sedimentation tank handling 300 meter cube per hour or water flow, ideal settling velocity is found out to be 25 meters per day. Dimensions of the tank are 42, 11, and 3. You have to check for score velocity, assuming settling of unigranular sand particles. Specific gravity as 2.67. First of all, what we should do is the settling velocity is ideal. Ideal means 100% settling condition. That is nothing but V naught must be same as Vs. Under ideal settling condition, V naught is equal to Vs, and Vs is can be obtained from Stokes law. It can be calculated on Stokes law using the given data. So again, I'm doing all the calculations here, and substituting here in Stokes law as mentioned in the previous problem. and d square you have to find out. So this settling velocity is there now calculated. Specific gravity is 2.67. T is given as 20. So 20 centigrade we are assuming here. It's not given. If not given, we'll assume the ideal temperature of the water is 20 centigrade. So therefore, D is equal to 0.018 millimeters. So ideal settling pH is equals to TV, time of horizontal travel must be same as time of vertical travel. That means L by VH is equal to H by Vs, or VH is equal to Vs into L by H. VH is equal to 25 to 42 by 3, which is 350 meters per day, which is equal to 0.004 meters per second. This we have calculated from the equation, right? So now score velocity will be calculating from the general equation. Vd is equal to 8 beta g by f, etc. I am substituting all the values. Non-unigranular sand particles means beta is equal to 0.04. So we can assume the F value, Darcy friction factor, as 0.03 and then substituting here. Then I calculated this value as 5.6 centimeter per second, or 0.0 uh, 5.6 meters per centimeter per second. VH is equals to 0.004 meter per second. So that means what we are having is VH is less than VD. So that's the ideal condition. Sometimes we need to encounter the settling velocity of the particles greater than 0.1 mm, because Stokes law is valid only for 0.1 mm. Suppose here we have a case to calculate the settling velocity of the particle 0.04 centimeters. So 0.04 centimeters means 0.4 mm here. So it is greater than 0.1. So Stokes law is not applicable. So what should we do? We have to go for iteration process. First of all, we have to assume that the settling is now following Stokes law. We can use any of these two equations depending on the given data. So now I'm calculating V using Stokes law, and specific gravity is equal to 2.67, and using the formula V is equal to 418 d square, etc. And now I'm calculating this as 162 millimeter per second, which is equal to 16.2 centimeter per second. Now we have to check the Reynolds number and coefficient of drag. So now if I check Reynolds number, taking the absolute viscosity at 25 centigrade as 1 into 10 to the power of minus 3 Newton second per meter square. What I got is 72. It is greater than 1. So for less than 1 only laminar flow. Greater than 1 up to 10,000, it is transition flow. For transition flow, the CD value is not 24 by RE, but is having some two additional parameters, 0.34 plus 3 by root R. So therefore, I have to calculate the CD value once again using this formula, which is RE is equal to 72. So 24 by 72 plus 0.34 plus 3 by RE square root 1.027. So now, what exactly is happening now afterwards is once again, we have to go for the standard generalized velocity formula. This is discussed during the Stokes law. So here, the CD we obtained the denominator. This CD, what we have done, we have assumed the laminar flow and the CD is equal to 24 by RE and substituted that to get the Stokes law. So now we are going for the original equation. The CD is now you have to calculate this CD, you have to calculate using the CD for transitional flow. So now here in this fourth step, the velocity we have to calculate once again using CD value, what is obtained now. So CD value 1.027 obtained, and using this equation, I am getting this value as a 0.0922 meter per second. and check Reynolds number for this value. What I got is 40.99, greater than 1. Again, transitional flow. So once again, I put this velocity in the Reynolds number, and the Reynolds number, what I got 40.99 I got, and for this 40.99, then Reynolds number, I will calculate CD value. What I got here 1.394, and then using CD as 1.394, and then I will be calculating once again the velocity using general formula for these two values. These two values. What I got is what is that? 0.0792 meter per second. Now you see here, initially you have started with some value. First iteration we got this much, 0.0922. In second iteration we got 0.0792 meter per second. Once again we'll check for Reynolds number. For this velocity, it is still greater than 1, so transitional flow. And for this Reynolds number, we go with the CD for transitional flow. Then once again I got 1.527, and then once again I'll check the velocity with these two values of 1.527 and Reynolds number 35.2. What I got is 0.0756. So now what we have to look at is the values of velocity obtained in two successive iterations. Here 0.0922, 0.0792. The gap is slightly higher. But when you look at the second and third iterations, 0.0792 and 0.0756, the gap between these two velocities is much, much smaller. Even if you go for a fourth iteration, you may get even slightly a lesser value than this. So we can stop the iteration once we check the values of velocity which are closer between two successive iterations, and then we'll assume that the velocity of this particle as 0.0756 meters per second. The only thing you have to remember, what are the equation you are using, what are the values which are given in that equation, and that should be followed. For example, when you are following this equation, V is equal to 418, the diameter should be in millimeters. Diameter should be in millimeter, always remember. And V should be in millimeter per second. So again, that consistency of your units must be followed.